Okay, the equation of a line in 3 dimensions is R equals R naught plus VT. Okay, where R naught is a vector and V is a vector, okay, and T is a scalar. Okay, so vector, vector, scalar. Okay, so R naught is the vector from the origin to a known point on the line. So R naught is a vector from the origin to a known point on the line. Okay, we'll call that known point P naught, X naught, Y naught, Z naught. Okay. V is a vector from the origin parallel to the line okay, and T is a scalar, okay, or a multiplier. Okay, so let's set this up. Oh. Draw. There we go. Okay, so let's take a look here. See what's happening. Okay, and I'm gonna just draw a line, okay, kind of our random line here. Okay, maybe I'll put that in purple. Okay, there's my line. Okay. And I want the equation of the line. Now this, again, this is in 3 space. Okay, so think of this as, okay, this is a line in 3 dimensions. Okay, so 3 dimensions. So this is a line in space. Okay, so the first thing that we want to do is we want to locate a point on this line. Okay, so let's locate just a random point on this line. We'll call this point P. Okay, that's just point P on the line. So we need a point and we need a vector. Okay, we need a point and we need a vector. Okay, so the point that we're going to get is going to originate from the origin. Okay, the vector that goes from the origin to this point on the line, we're going to call R. This is going to be called P naught. Okay, P naught. And so we're going to call this from the origin to P naught. We're going to call that R. Okay, so maybe we'll make R in black. Okay. So that's R right there. Okay, so this is R naught. Okay. Okay, so as we travel along and we get another point here, okay, any point, well, we need to know what's parallel to this line. We need a vector that's parallel to this line. Okay, so that starts at the origin. So I'm going to draw a vector that's parallel. Okay, this is going to be V. Okay, a vector that's parallel. What was this? This was 26 degrees. Okay, so from the origin, 26 degrees. Okay. Okay, and we need it parallel. Okay, so I'm going to call this V. Okay, this is vector V. It's in the same direction as the line. Okay. Okay. And so if we can get vector V and we can get vector R naught, okay, then we can write the equation R, okay, of this line. R is a compilation, okay, R is a compilation of R naught, the starting point, and then any other point on this line. Okay, 2 points define a line in 3 space. And here we're saying that these 2 points, okay, are going to be one point that's going from one vector that's going from the origin to a point. And then we want the vector parallel here. Okay. The vector parallel. Now, why? How is this working? Okay, to give me this R, it's plus VT, right? VT. Okay, so let's think about this for a second. Okay, so let's look at VT. VT is a scalar. That means that I could scale up and down my vector any way I want. Right? I could scale the vector up and down. If I let t equal 1, then what is this going to look like? Well, it would look like this. I would get P naught, and then I would get V to be exactly the same, length as I would get VT to be exactly the same length as V. So what is that length about? Is this just a continuous roller that goes on forever and ever? I guess so. Okay, so that length is about, well, it's almost exactly 2 inches. Okay, so let's go up here 2 inches. And let's put this point here at 2 inches. And I'm going to call that point Q, okay? Or P, it really doesn't matter. I'll just call it point Q. Okay. And I'm gonna make this vector here. Okay, and I'm gonna call this vector A. Vector A. This is a vector A. Well, what is that vector A? Isn't that in the same direction as V? Isn't that really just vector V if t was equal to 1? Yeah, it would be, okay. But I don't have to let t equal 1. We'll get to why we don't have, why this is going to create a line. Okay, so what is R naught plus V naught, or VT, I guess you could say. What's the addition of this? Well, it's this guy here, Okay, we're going to add this vector to this vector, right? We're going to do vector addition. And we're doing tail-to-tail addition, so it's a parallelogram. Okay, so we're going to do parallelogram. Okay, so I'm going to get rid of this line here. This is just, that's an auxiliary line. Okay, just to let you guys know. Okay, but how would I add these? Well, I would get this parallelogram here. What is that? 59 degrees? 59 degrees. Okay, so move this over just a little bit. Okay, ooh, didn't want to do that. Okay. So do you see my parallelogram now? You see my parallelogram? So if I add these two vectors, r and v, okay, r and v, what am I going to get? I'm going to get this vector here. I'll put this in gray. Okay, just the resulting vector. Okay, the resultant vector. Let me put this in gray. Okay, here's the resultant vector. Okay, and what is this? This is r. That's vector r. Okay, for that one point. Right? Isn't that vector r for that one point? Because didn't we add r naught and v together? And we got this guy. So we could say that A is equal to R naught plus V. That's what A is equal to, right? That's what A is equal to. But I could let A vary. Let A vary by allowing A to equal R naught plus V of t, right? So if you let the size of my vector here, V, vary, go positive to whatever point or negative to whatever point, if I let t be 2 or 3 or 1.5 or 7 or whatever, aren't I allowing myself to go to any point on this line? Right? Say t was equal to -3. Well, that would be this point. T equals -3. What if I wanted t to be 1/2? Well, that would be this point. What if I wanted t to be 1/3? Well, that would be this point. You see that? That this, by allowing t to vary, gives me every single point on that line. Okay, Q was one specific point. Okay, Q was one specific point, and A was one specific vector to go from P to Q. But if we let A vary, then we get R is equal to R naught V of t. Okay, we just let R is gonna, okay, every single point on that line. Okay. Okay, let's look at the parametric form of this. Okay. Parametric form of a line. Okay. So I'm going to let P naught equal X naught, Y naught, Z naught. I'm going to let Q equal X, Y, Z. I'm going to let Q vary now. Okay, and I'm going to let V equal A, B, C. So again, it's R is equal to R naught plus VT, right? VT, okay. So what's R naught in this case? Well, R naught is this point, okay, actually R naught is not the point, it's the vector. It's the vector. So R is equal to vector x naught, y naught, z naught, plus v. What's v in this case? V is ABC times t. We're going to let t vary. Okay. Let t vary there. Okay. So now let's just do some vector calculation here. R is equal to x naught, y naught, z naught, plus AT, BT, CT. Okay, so R is equal to, now let's add components. This is going to be x naught plus AT, y naught plus BT, and z naught plus CT. Okay. Okay, so we could say that our x component, okay, our x value in our line is x is equal to x naught plus AT, y is equal to y naught plus BT, and z is equal to z naught plus CT. Okay, that's the x component, that's the y component, and that's the z component. Okay, and this is the parametric form of a line. In 3 dimensions, 3 dims. Okay, if we solve for t, in each of these, okay, we could say that x minus x naught over a is equal to y minus y naught over b is equal to z minus z naught over c. Okay, and these are called the symmetric equations. Of a line. Okay, and again, this is given a point and a vector. The point was at x naught, y naught, z naught, and the vector was at a, b, c. Okay, and that vector is originating from the origin. Okay. If v equals r1 minus r naught, what is that? r1 minus r naught. That means that when t is equal to 1, we have this guy, right? Okay, so r naught is when t is equal to 0. R1 is when t is equal to 1. Oh, okay. So, okay, so let's see what's going on here. Okay, actually, I don't like that. I don't like r naught being t is equal to 1. Okay. Let's rewrite that definition. Okay. So what's the vector v in this case? If we have r1, let me draw the picture here. Okay, real quick. Okay, we have r1, okay, on this line, or r naught, sorry. We have a r naught, and then we have r1. Okay, so we have this point here, and we have this point here, and it's on this line, okay, in 3 dimensions. So what is r1 minus r naught? What is that? Well, okay, that's this vector here. Okay, R naught minus R1 minus R naught. Remember that triangle, right? When we have the triangle here, we go R1 into R naught, okay, and we subtract. That's the distance between P naught, we'll call it, and P1. Okay, that's the distance between P naught and P1. Okay, after one, you know, it's the next value up. It's after T is equal to 1, basically. Okay, after 1 unit of time or 1 unit of measurement, however you want to think about it. Okay, so, okay, if this is true, okay, then what happens to the equation of the line? Well, then R is equal to R naught plus V of T, right? And so R is equal to, okay, R naught plus, well, what's V? V is R1 minus R naught. Okay, so R1 minus R naught, that's this vector here. Okay. So R1 minus R naught times T. I'm going to distribute the T. So R naught plus R1 minus R1T minus R naught T. R naught minus R naught T plus R1T. Okay. So now I'm gonna pull out this R naught. So this becomes R naught times 1 minus T plus R1T. Okay, so I'm gonna rewrite this a little bit more. I'm gonna say that this is R of T is equal to 1 minus T times R naught plus T times R1. Now let me explain what's going on here. Okay. For 0 is less than T is less than or equal to 1, this is the line segment from P naught to P1. Now, why is this? Okay, because we're saying that V, okay, the vector V here, okay, R1 minus R naught, right? That's the vector we're using. Okay, and that's going to give us a line segment. We're only allowing T to go from 0 to 1. Okay, where at when T is equal to 1, or sorry, when T is equal to 0, we get R naught. So maybe we'll do R sub n, or let's do it this way. T and then R sub n, right? If T is equal to 0, this would be R naught. When does that make sense? That R would be equal to R naught when T is 0. Well, yeah, it would make sense, right? You just plug in 0, right? If T is 0, then you just get R naught. Well, what about if T is 1? What are you going to get? Well, you're going to get, you know, R naught plus V, okay, or R1, R sub 1, okay? So you're going to get 1 unit out for V. But well, what are we saying V is? Well, we're saying V is the distance, is the vector between the vector R1 minus R naught. Well, why is that? Because remember, our triangle, right? So our triangle here, right? So if we go like this, then, and we say that this is B and this is A, right? Or sorry, A and B. Let's go A and B here. Then what is this resulting vector? Isn't that just A minus B? So if this guy here is is R1 and this is R naught, after t is equal to 1, I start at R naught and I go to R1, then after 1 unit, well, what's the distance here for V? Well, the distance there for V is R1 minus R naught. That's the distance for V. So when at t is equal to 1, we get R is equal to, okay, R naught plus V, but what was V? V was R1 minus R naught, right? Times 1. So this is going to check out that the R naught is going to cancel out. R naught plus R1 minus R naught, those cancel out, and I'm just left with R1. Okay, when t is equal to 1, I get R1. Okay, but if I let these be my endpoints, right? P naught and and P1, call that P1. If we let those be my endpoints, then how would I get every single point in between here? Well, I would only allow t to go from t equals 0 to t equals 1. And that would be my equation of a line segment. Okay, let's do a couple of examples with this. Okay, so let's keep in mind that R is equal to R dot plus V of t. Okay, X is equal to, okay, X naught plus A of t. Y is equal to Y naught plus B of t. And Z is equal to Z naught plus Z of t. Okay, these are my parametric equation of a line. Okay, this is my vector equation of a line. Okay, so vector equation. This is parametric equations. And what was it? It was x minus x naught over a is equal to y minus y naught over b is equal to z minus z naught over c. These are the symmetric equations of a line. And then what was the equation of a line segment? Line segment, okay, that was R of t is equal to, okay, 1 minus t times R naught. Is it minus or plus? Yeah, it's plus t times R1. Okay, so that's a line segment. So we're going to utilize this here for a second. Okay, so let's look at number 1. Oops. Let's look at number 1 here. Okay, so number 1 says find the vector equation and parametric equations for the line that passes through point 513 and is parallel to vector I plus 4j minus 2k. So we want the vector that's parallel and we got the point. Okay, so what's the point? What's P naught? P naught is 513. Okay, what's vector V? Vector V is 1, 4, negative 2. Okay, so we have R is equal to R naught, which is 513 plus VT. Okay, R naught plus VT, right? So V is 1, 4, negative 2, okay, times T. Okay, so R is equal to 5 plus 1 is 6. This is 6. Sorry. Or no, you know what? I need to distribute the T first. My bad. So this is 5, 1, 3 plus t, 4t minus 2t. Okay. Okay, so this is equal to 5 plus t, 1 plus 4t, and 3 minus 2t. Okay, so this is my vector equation of the line. Okay, the parametric form of this is x equals 5 plus t, y equals 1 plus 4t, and z equals 3 minus 2t. That's the parametric form. Okay, of the line. That's it. I'm done with that one. Okay. Now we could put this in a standard basis form as well. Okay. Standard basis form. Instead of component form, we could write R equal to 5 plus ti plus 1 plus 4tj plus 3 minus 2tk. We could do that.
Sorry, Professor, can you scroll up a little bit?
Up or down?
Or down, I guess. Thank you.
Okay, so 3 minus 2tk. So you could write it in standard basis form either. Okay, as well. Okay, number 2. Okay, find the parametric equations and symmetric equations of the line that passes through the points A, 2, 4, negative 3, and B, 3, negative 1, 1. Okay, so find the parametric equations and symmetric equations of the line that passes through these 2 points. Okay, so let's let R naught be equal to 2, 4, and negative 3. Okay, so R naught be 2, 4, and negative 3. So how would I find V, vector V? Well, vector V is going to be the difference between A and B. Okay, I have these 2 points out in space, and I want a vector between them. Well, how do I find the vector between point A and B? Well, I just subtract the components. Okay. So vector V is going to be 3 minus 2, comma, negative 1 minus 4, comma, 1 minus negative 3. Okay, that's vector V. This becomes 1, negative 5, and 4. So that's vector V. Oh, okay. So now let's see what we get here. Okay. So R is equal to R naught plus VT. Okay, that's the equation of a line. Okay, R naught is 2, 4, negative 3 plus V, which is 1, negative 5, 4, T. Okay. So this is going to be 2 plus T is X. Y is going to be 4 minus 5T. And Z is going to be equal to negative 3 plus 4T. Those are my parametric equations. Now let's solve for t and get our symmetric equations. Okay, let's solve for t in these. Okay, so this one, t is going to be equal to x minus 2. I'm going to put it over 1. Okay, just for right now. Okay, you don't have to put it over 1 because that's just going to be x minus 2. But I'm just going to put it over 1 because I just want to make sure that it's in the same format. Okay, this is going to be y minus 4 over negative 5. Y minus 4 over negative 5. And this one is going to be t plus 3, or sorry, z plus 3, not t, z plus 3 over 4, right? Z plus 3. Now I'm going to set all these equal to each other. I'm going to say x minus 2 is equal to y minus 4 over negative 5, which is equal to z plus 3 over 4. Okay. That's
good. Isn't it 4 minus y over 5? Oh.
Oh, no. I like mine better, but you can do what you want to do. Okay. Okay, number 3. Okay, given x equals 2 plus t, y equals 4 minus 5t, z equals negative 3 plus 4t, where does the line intersect the xy plane? Where does this line intersect the xy plane? Where does that line intersect the xy plane? Okay, well, what do we know about the xy plane? What do we know about the xy plane? Any ideas here?
Z is 0.
Yeah, thank you, Armando. Z is 0. Okay. So yeah, if z is 0, then isn't 0 equal negative 3 plus 4t? So wouldn't t equal 3/4? Right? So then
Yep.
couldn't I figure out what x and y are? Isn't x equal to 2 plus 3/4 or 2 3/4? Isn't y equal to 4 minus 5 times 3/4? Okay, which is equal to what? 4 minus 15/4. So 16 minus 15/4. 16/4 minus 15/4 is 1/4. So where does the line intersect the xy plane? Right? Where does this line intersect the xy plane? Well, where is it going to intersect the xy plane? It's going to intersect at an x value of 2 3/4, a y value of 1/4, and what's the z value?
0.
0.
0, exactly. It's not a trick question. Okay, it's 0. Does that make sense? So this is going to be that point there where it crosses the plane, the xy plane. Okay, where that line goes through the xy plane is going to be at this point. Okay, let's talk about what a plane is. a plane is described as, by a point on the plane and the orthogonal vector through that point called the normal vector. Okay, so it's a point on a plane. Okay, normal vector, or little n for short. Okay, lowercase n for short. The normal vector to the plane. Okay, so we have a plane. Okay, and that plane is defined by a point and the normal vector to that plane. Okay, so this is P naught, and that's n. Okay, P naught and n. Okay. If we think about what's happening on the plane here, okay, we have this point, right? That point, and say the origin is here. We're originating from the origin, right? So if we have a point P naught, then this is going to really suck. Let me get my ruler back out. Okay. Come on, move ruler. There we go. Come on. What the heck? Oh, I'm just move this up. Doesn't like it when I get to the edges. Okay, so this guy is R naught, right? That guy's R naught, right? Okay, and so this guy, okay, we'll say is R. R. He can be anything I want him to be. Okay, but when I do my cross product on this, when I do my right-hand rule from R naught cross R, that equals my normal vector, right? That equals n, okay? So R naught cross R goes to n. Okay. Now, what's the dot product? Okay, what's the dot product to a normal vector? What's the dot product from a vector to a normal vector? Anybody remember?
0.
Yeah, it's 0, exactly. It's 0. It's 90 degrees, right? What's the cosine of 90 degrees? It's 0. So we could say that n, okay, n dotted with any vector on this plane, okay, any vector on this plane whatsoever, okay, is equal to 0. Okay, is equal to 0. Now I'm gonna choose a specific vector on the plane. Okay, or basically what I'm going to do is I'm going to say, well, what is this vector here? What's this vector? Anybody know what that vector is? There. Any ideas? In terms of R naught and R, what would that vector be?
R naught plus R.
No.
Is R minus R naught?
Yeah, let's think about this for a second, right? So that's a triangle that I created, head to tail. Okay, head to tail. So we're going, right? We're going this way. So I'm gonna take. Okay, let's think about this for a second. If we did this guy, and then we did this guy here, right? So we said A, B, and then what's the vector between them? That would be A minus B, right? Okay, so I'm going to call this guy X. Okay, I'm going to call that guy X. So I know that R, well, I know that that this guy is X X minus R naught equals R, right? Okay. Is that right? X minus, so A minus B is equal to R, yeah?
Is it R naught minus X?
Is it R? It should be. Let me think about that for a second. Not where the not with the direction of the.
Because the arrow point down for R, so it's R naught minus X is equal to R.
Okay, so again, we have A and B, right? If we have this arrangement here, okay. Oh no, this is, yeah, this is A and B. Then this guy here is A minus B, right? And so here's the arrangement we have here. R is equal to X minus R naught. I'm pretty sure that's correct. Okay. Except for whatever reason, it doesn't look right. Let me think about this for a second. Oh, you know why? Because I screwed up. That's why. I don't like this. I screwed up. The reason I screwed up was this. This is R, and this is X. Yeah. Okay, so now what is this? Now what is X? X is now R minus R naught. That makes sense. Okay, X is R minus R naught. Because that should be R, right? Because R just represents any vector to the line. Does that make sense? And X is that distance. Okay, so we've got a line on this plane. Yeah. So I just reversed it for whatever reason. Okay, so that makes sense. Okay, so now what I'm going to do is I'm going to say n dotted with R minus R naught is equal to 0. Okay, I'm going to do distribution of dot product. So n dot R minus n dot R naught is equal to 0. And I'm just going to say, n dot R is equal to n dot R naught. Sorry, n dot R is equal to n dot R naught. And we say that this is the vector equation of the plane. Vector equation of the plane. Okay, so that's the vector equation of the plane. Okay. Okay, so let's let n equal a, b, c. Okay, let's let n equal a, b, c. Okay, so now what is this going to become? Okay, this is going to be, let's go back a step. Let's go back to this step here. Okay, we would have n dot r minus n dot r naught is equal to 0. And so we're going to say ABC dotted with r minus ABC dotted with r naught. Okay, r naught is equal to 0. Okay, so how would we represent r though? R is all the values that could be on that line. All the points that could be on that plane, okay, in some sort of line is r. So r, I'm just going to represent r as x, y, z. And r naught, I'm just going to represent as a specific x naught, y naught, z naught. Okay. And so this becomes ABC. Easy as 1, 2, 3. Okay, x, y, z minus ABC dotted. These are dotted, by the way. Dotted with x naught, y naught, z naught is equal to 0. Okay, so now let's dot these. Let's see what happens. Okay, so this is going to become ax plus by plus cz minus parentheses. Okay, ax naught plus by naught plus c z naught, okay, is equal to 0. Okay, let's distribute the negative and put like terms next to each other. So ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. I'm going to factor out the a, b, and c here. A times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. And this is the equation of a plane. Okay, this is called the scalar equation of the plane. Scalar equation of the plane. And this is the one we're really going to use. Okay, this is the one that's most important. Scalar equation of the plane. Okay, that's the scalar equation of the plane. Okay, through the point P naught, x naught, y naught, z naught, and normal vector, and with normal vector, okay, ABC. So this is a vector, A, B, C. So again, all we need is a point and a normal vector, and we can find the equation of a plane in 3 space. Okay, if that makes sense. All we need is a point and the normal vector. Once we have the normal vector and a point. Now, here's the deal. We're often not given the normal vector. So what could we do if we're not given the normal vector? What if we're just given 2 points? What if we're just given 2 points on a plane? Let's look at a plane here. We're just given 2 points. I'll call this point P naught, and I'll call this point P1. Okay, we're given 2 points on a plane. How could we create a normal vector? How could we create a normal vector? P1, well, couldn't I just do a cross product here? Right, cross this into itself. P1 cross P naught. And wouldn't that give me a normal vector? Right? Okay. Okay, and I don't need the normal vector to go through the point. Okay, I just need a point and a normal vector. Okay, I just need. Okay. So there I would have 2 points and a normal vector, and I can just use one of the points with the normal vector, write the equation of the plane. This tells me that equations of a plane are not unique. Okay. Okay, they're not unique. Okay, let's do an example of this. Okay, I don't know, I forgot what number we're on. Number 3, 4, on number 4. Okay, let's go back to number 4. So number 4 here. Okay, find the equation of the plane that passes through points P146 and Q -2, 5, -1. And R, okay, 1, -1, 1. Okay, so 2 points to find a line, 3 points to find a plane. Oh yeah, I think that's what I was missing here, was the third point. You have to have a third point. Yeah, makes sense. Okay, so P naught, P1, and P2. Okay, yeah. So 3 points to define a plane. Okay, so what I need to do here, okay, is I need to find, okay, the normal vector. So how could I find a normal vector? Well, if we have points P, Q, and R in space, P, Q, and R in space, 3 space, then if I look at the vector PQ and I look at the vector PR, couldn't I cross those? Right? Couldn't I cross those and then get N? Right? Because I need a point and I need a vector, normal vector. So what I'm going to do here is I'm going to take PQ and cross it with PR to get N, my normal vector. Okay. So what is PQ? Well, that's just going to be the difference here. So let's look at vector PQ. That's going to be -2 minus 1. That's going to be 5 minus 4. And that's going to be -1 minus 1.
should be -1 minus 6.
I screwed up somehow. How did I do that? It's -1, yeah, minus 6. I was looking at the wrong one. Okay. All right, yes, yes. Good, okay, so this is okay, good. Okay, so PQ is equal to -3, 1, and -7, right? -3, 1, and -7. Okay. Okay, what about PR? What's that one going to be? PR. That's going to be 1 minus 1. That's going to be -1 minus 4. And that's going to be 1 minus -1. Okay. All right. No, 1 minus -6. Or 1 minus 6. Sorry. Okay, 1 minus 6. So what is this going to be? This is going to be 0, -5, -5. Okay. So now what do I need? I need PR crossed with, right, PR crossed with PQ. Crossed with PQ. Okay, so IJK, PR 0, -5, -5. PQ is -3, 1, and -7. Okay, so what's this going to become? This is going to become 35. Okay, this is going to be 35 plus 5, which is 40. So 40i. This is going to be positive 15, but there's a negative, so -15y, -15j, right? -15j. And then k is going to be positive 15k. Okay, so that's the cross of that one. Okay, so what is A in this case? We want our vector, right? Vector. So what is A? A is 40, B is -15, and C is positive 15. Okay. So let's look at our equation. Our equation was A times x minus x naught plus B times y minus y naught plus C times z minus z naught, okay, is equal to 0. That's the equation of our plane, where A, B, and C are orthogonal to the plane. So A, B, and C are orthogonal to the plane. Okay, so this is going to be 40 times x minus x naught. Well, what do we want to use for x naught? Well, we could just use P, since that's where the orthogonal is originating. So let's just use P. Okay, it really doesn't matter. We could use any of them, but we're going to use 146. Okay, so 40 times x minus 1 plus -15 or minus 15 times y minus 4. Okay, plus 15 times z minus what is this? 6. Okay, is equal to 0. Okay, so now let's distribute. And we get 40x minus 40 minus 15y plus 60 plus 15z minus 90 is equal to 0. So 60, -30, -70, right? So this is 40x minus 15y plus 15z equals, okay, or we could say minus 40 is equal to, or is it 10? What do we got here? -90. Oh, is this a plus? Is this a negative one? I don't know what I did. No, that's right. So it's 40, right? 40 x. Yep, that's right. Okay, minus 40. Yeah, that's right. Okay. Okay, so yeah, that's minus 70, right? So minus 70? No. What's wrong here? No, that's right. That's right. Yeah, that is right. Minus 70 is equal to 0. Okay, messing up on my arithmetic. Okay, so we could leave it as this, or we could toss this to the other side. So 40x minus 15y plus 15z is equal to 70. That's the equation of a plane. Okay, so that's the equation of the plane there. Let's see what else I want to talk about here. I think that's about it.
Professor, can we simplify the equation also?
Which one?
The
This one?
equation of the plane.
This one here?
No, the result, the last
How do
equation.
you want to simplify it?
Divide them by 5?
Divide them all by 5? Oh, yeah,
Yes.
sure. You could do
Okay.
that. Yeah,
All right.
it's the same plane.
Yes. Okay.
Yeah, that's fine. Okay. Two planes are parallel if their normal vectors are parallel. Okay. So if the angle between two normal vectors is parallel, okay, then it's parallel. The distance from point P1, x1, y1, z1 to a plane ax plus by plus cz plus d is equal to 0. Okay, so d was kind of all of that constant, right? So d is just this constant value that we come out with for, this is the general equation of a plane. Okay. Right? So a general equation of a plane is ax plus by. You leaving? You do that side? Okay. Okay, so this is the general equation of a plane. You can see that, you know, if we really wanted to reconcile all the constant values, we could by getting this general equation of a plane, but we just call it d for all of those constants. Okay, all the constants just combine into one big constant. Okay, so the distance from a point to a plane. Okay, so there's a point out in space here, and we have this plane, and the distance, the shortest distance, okay, is d is equal to the magnitude, okay, it's the magnitude of a x1 plus by1 plus cy2, or sorry, z1, plus d, magnitude of that, over the square root of the, it's just the magnitude of the vector, okay, vector v, a, b, c. Okay, it's the distance, okay, along to that plane over the magnitude of the normal vector. Okay, so the normal vector here, n. Okay, and that's a squared plus b squared plus c squared. Okay, so it's the magnitude of that guy. It's really the absolute value because these things are all going to be values. So absolute value of the top over the magnitude of the normal vector, ABC. Okay, let's move on to 12.6. Okay, cylinders and quadric surfaces. Okay, quadric surfaces. Get rid of my ruler for right now. Okay, so what is a cylinder in 3 space? Okay, a cylinder in 3 space, okay, is a surface, okay, that consists, okay, of all lines called rulings that are parallel to a given line and pass through a given through a given plane curve. Okay, so okay, so let's see what we got here. Okay, so you would think that a cylinder looks like this, but that's just one type of cylinder. Okay, that is just one type of cylinder. That's your typical cylinder, right? Okay, it either looks like that or it looks like this. Okay, but it doesn't have to look like that. These are the rulings that are all parallel to each other. Okay, it could look like this. Okay, in 3 space. It doesn't have to be a circle. Okay, we could have a parabola. We could have a parabola be a cylinder, as long as it's going all in the same direction. Okay, and so we have all of these rulings. Okay, and so we have these guys here. Okay, and you can have a separate color on the inside, I suppose, to give it some contrast. Okay, but those are all the rulings. Oops. Okay. Redo that. These are all the rulings inside. Okay, all parallel, all parallel. And a cylinder will go off in infinite direction. Okay, it goes off in infinite direction. Okay, but it's all in a line. It's all in a line. Okay, it's the surface that contains of all the lines that go in one direction. Okay. Okay, so let's look at this cylinder here. Okay. Let's say that z is equal to x squared. Z is equal to x squared is this cylinder. Why is it this cylinder? Because we have x, y, and z, right? X, y, and z. Here's z here, right? Oops. Z is going up. X, Y, and Z. And so is this cylinder. And so we have Z equals X squared. Notice what's missing. What's missing in my equation?
Y.
Because I asked, that's why. I'm just playing.
Okay.
Okay, it is Y. Yes, it is Y. Y is missing from my equation. So what does that mean? That means Y can be anything it wants to be, right? Y can be anything it wants to be, which makes sense. Okay? Because if this is going infinite direction, in the Y direction, then that would make sense that Y could be anything. Hopefully that makes sense. Okay? It's like having a line x equals 3. What can Y be in this equation? Anything you want it to be. So if Y can be anything you want it to be, then isn't this the line x equals 3? Can't Y be anything you want it to be? Yeah, so it creates a line. If you just have z equals x squared, right, in 3 space, right? If you were to have this in 2 space, if you were to say, oh, y equals x squared, well, isn't that a parabola in 2 space? Yeah. Okay. Let's do it like this. Let's do it like this. Let's create the xy plane here, right? The xy plane. What would this look like in the xy plane? Y and x. Wouldn't it look like this? Does that make sense? Look like that, right? Probably not like that. Probably a little bit better than that. But does that make sense that that would look like that in the xy plane? Right? If we're just looking top down onto this, you're like, oh, that's the positive x direction. That's the positive y direction. That's a parabola, right? That's a parabola we know. But now we have to designate, is this in R2 or is this in R3? Because if this is in R3, then what happens? If this is in R3, then I've got a third axis to contend with. Right? Make sense? Does it make sense? You get it? Now we got a third axis. Okay, so R3. We're not dealing with R2 anymore. Okay, no R2D2s anymore. It's all R3s. Okay, so it's a cylinder. The cylinder is in R3. Okay, could I have made this a circle? Should I? Sure, I could have made it a circle. Okay, then it's what you think of as a typical cylinder. Okay. So let's look at this guy here. Identify x squared plus y squared equals 1. What is that? X squared plus y squared equals 1. What is it? What is it?
A circle?
No, it's a cylinder. I'm just kidding. It's a cylinder. Why is it a cylinder? Because we're dealing in R3. It's the what you think is the equation of a circle, but you're wrong. Right? I'm just playing. right? You think this is a circle, but it's in R3. So now what happens? It goes like this. In infinite direction in both sides. And we've got our rulings here that make up those guys there. Okay, makes sense? Okay, let's talk about quadric surfaces. Okay, quadric surfaces. Okay, we need to talk about what a quadric surface is. Okay. What was a conic section? A conic section was all graphs up to 2 variables with a second degree power. Right? Conic section was all graphs up to 2 variables with a second degree power. Does that make sense? What was a conic section? They remember what the conic sections were, right? We took a cone and we just sliced the cone. Right? If we slice it like this, we get a parabola. If we slice it like this, we get an ellipse. Okay, if we slice it like this, we get a circle. Does that make sense? Those are why they're called conic sections, because you just slice up a cone and you get a parabola. All right, you get this second degree. You get a parabola. Sure, can't talk. Parabola y equals x squared. We could get an ellipse. This would be, we could get a circle. X squared plus y squared equals 1. An ellipse would be like x squared over 4 plus y squared over 4, or over, we'll say 9, is equal to 1. We get an ellipse. We could get a hyperbola. Okay, x squared over 4 minus y squared over 9 is equal to 1. Okay, I think that's it. Okay, we get these interesting second degree powers, but this is only in R2. Well, quadric surfaces are the exact same things, but in R3. Okay, they're the second degree polynomials, but up to 3 variables this time. 3 variables this time. Okay. For a conic section, the general equation for a conic section looked like this. Ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. Okay, we could have all of those different combinations. Okay, and that's a conic section. Okay. For a quadric section, quadric surface, sorry, quadric, because these are 2 dimensions. For the quadric surfaces, we just allow all the combinations for 3 variables up to the second degree. So for a quadric surface, okay, it could be a x cubed. Or sorry, not x cubed. Ax squared plus by squared plus cz squared, so we've got a z now, plus dxy plus exz plus fyz, okay, plus gx plus hy plus iz plus j equals 0. So all the combinations. Let's zoom in on that. All the different combinations here. Okay, so what are traces? Okay, let's talk about what a trace is. Trace, okay, a trace.
I'm sorry. What does it say after X, Y, Z plus?
Why what?
After F, Y, Z plus, is it 5X? I'm sorry.
Huh?
It's GX.
I'll just leave it up here.
Oh, okay. Thank you, hon.
Okay, traces are, okay, think slices, okay, are planes parallel to the axes, to the coordinate planes. Okay, so traces are special rulings. They're special rulings and they're only in the X, Y, and Z direction. Okay, they're only in the X, Y, Z direction. They're parallel to the coordinate planes. They're special types of rulings, think slices. Okay, so if I were to, if I look at a sphere here, okay, if we were to look at a sphere, where would be the traces of this? Well, it would be on the coordinate planes, okay? So it would be parallel to the coordinate plane. So I could actually have I'm gonna put this in a different color. I could actually have a trace here. That was supposed to be a different color. Hello. Okay, we can have a trace here. Okay, we could have a trace here. Okay, and then, so that's in the Y direction. That's the Y plane. This is the XZ plane. What's the other one? Oh, it's the big one, the big circle. This would be a trace. Okay, so those are three traces. And what do they allow me to do? They allow me to trace the surface. Those traces allow me to trace the surface. Okay, so this trace is parallel. This is YZ and X. This trace is parallel to the YZ plane. That's the YZ plane trace. This guy here is parallel. That guy there. Oops. Oh, did it freeze? It froze. It froze. No. No freezing. No freezing, please. Let's see if I can get it to come back. Man, it is super hot. Super hot. I knew that was a possibility today. Excuse me. Thank you. I don't need 30 blushes, but I appreciate it anyway. Okay. You plug in the fan. So it's the problem with teaching for 4 hours straight is my tablet tends to overheat after a little while. After I don't know, what time did I start teaching? 2 o'clock. So it lasted 3 hours and 16 minutes. So and now I just have to reboot. So we'll take a little water break. I'm gonna go get a glass of water and I'll be right back while my system reboots because it was too hot. So I got it directly on the fan now. Actually, what I'm going to do is I'm going to pull up the PowerPoint while I'm waiting, because I was going to go to the PowerPoint anyway, because their drawings are a whole lot better than mine. Eventually, I got to use the PowerPoint anyway. So let's see. Yeah. I get it. Stop. Okay, so what do we got here? Let's bring this up. Santa Ana, Math 280, PowerPoint, Stewart, and this is 12.6. Okay. Yeah, that's good. Where's this guy? Sharing of the screen. Share screen. Okay. Okay. So here's the PowerPoint. Okay, it says use traces to sketch this surface. Okay, so let's use traces to sketch the surface. Let's use the traces, use the XY traces. Okay, so when we use the traces, we're going to let one of the variables go to 0. Okay, so, and we're going to use those traces here. Oh, it's back. Is it back? I'm back. Okay, good. Okay, so let me log in real quick. Okay, but here's the idea. Eventually, we're going to get here. Okay, this is called an ellipsoid. Okay, because of all the traces are ellipses. Okay, but we're going to eventually figure out, oh yeah, these are the traces, the slices. Think of them as slices, right? These are slices parallel to the X, Y, and Z planes. And you notice that it's symmetric with respect to each coordinate plane. This is a reflection of the fact that the equation involves only even powers of X, Y, and Z. Okay, you get mirror images here. Okay, so we're gonna graph this bad boy. Okay, and see what happens. Why does it never keep my credentials here? This makes me mad. Everything makes me mad. Sounds like a me problem. Okay. At sac.edu. Professor Holtman. Okay, am I back? I'm back with a vengeance. Start. We're almost done anyway, so it's all good. Okay, so yes. Okay, so I'm gonna scroll through all this stuff. All this wonderful math. Scrolling, scrolling, I'm scrolling. Okay, here we go. Okay, traces are parallel to the coordinate planes. There we go. Okay. So the idea traces are planes parallel to the coordinate. So let's do an example with this. Let's graph. Okay. Let's sketch. Okay. I don't know what number we're on at this point. I'm just going to throw up a 3. Who knows? Okay. Use traces. Use the traces to graph. Okay, or sketch. We'll say sketch. We're not really graphing. To sketch. Okay. I think slices to sketch x squared plus y squared over 4 plus z squared over 9 is equal to 1. Okay, so this is a quadric surface. Okay, why is it a quadric surface? Because it involves x, y, and z, and the highest power for this is the second power. Okay, now they don't all have to have a second power. They could have a first power. Okay, but they are the second power. Okay, that's the highest power here. And so what am I going to do? I'm going to use my traces. Now, how do I use the traces? The first thing I'm going to do is I'm going to let, let's see, which one do I want? Let's let x equal 0. Okay, let x equal 0. Then what do we get? Then we get y squared over 4 plus z squared over 9 is equal to 1. And what is that? Isn't that just an ellipse? Isn't that an ellipse where in the YZ plane? Well, where's the YZ plane? Let's look at our axes here. The YZ plane, oh, that's this guy over here, YZ plane. And so that's an ellipse where I go out 2 in the minor axes on the Y, out 2 on the minor axes, and up 3 in the major axes. This is not to scale. Okay. Right, and then out 2, and then 1, 2, 3. So one of the traces, the slices of this looks like this, right? So that's the slice. Okay, that's that slice in the YZ plane. Okay, so that's an ellipse, but I let x equal 0. Okay, so now let's let y equal 0. So now we're going to go y. Well, maybe we'll do let z equal 0 and see what happens on the floor here. Let's let z equal 0. Okay, and so we had z is 0, so this is going to be x squared over 1 plus y squared over 4 is equal to 1. Okay, so what does that tell me? That tells me that I'm going to go out 1 in the x direction. This is still an ellipse, but I go out 2 in the y direction. Okay, and so it's this ellipse now. Okay, so that's that ellipse. Interesting. Nice, nice, nice. Okay. And so now let's let y equals 0. Okay, so if y equals 0, then we get x squared over 1 plus z squared over 9 is equal to 0. And so that tells me that this is a third ellipse, okay, in the zx direction, okay, in the zx direction. Okay, so in the zx direction, and it's going to be 1 in the x's and 3 in the y's. So maybe I'll do this with another different color. Okay, purple maybe. And I'm going to say, oh, look, I'm going to go here, and then here, and then here, boom, like this. Okay, and so I get those traces, I get those slices. Okay, those slices, and that allows me to draw this ellipse. Make sense? Okay, what about this guy here? Okay, let's sketch this guy. We'll call this number 4. Okay, sketch z is equal to 4x squared plus y squared. 4x squared plus y squared. Okay, this is a quadric. Oh, this guy is called an ellipsoid, by the way. Ellipsoid. Why? Because it's just made up of ellipses, like a football. You know, just a squashed ball. Okay, what about this guy? What's this guy going to look like? Okay, well, let's let z equal 0. So we get 0 is equal to 4x squared plus y squared. That's kind of interesting. Okay, let z equals 0. We got 4x squared plus. Somebody have a question? Okay. So I could toss the 4 to the other side. Okay. So I could toss the 4x squared to the other side. This is 4x squared. That's a negative, right? Negative 4x squared equals y squared. That's kind of weird. So we could try to solve for y. The only problem is that we can't. So let's not use z equals 0. Z equals 0 is too weird. There really is nothing at z equals 0 because you're going to get an imaginary number. This is an imaginary result. You're going to get imaginary values at z equals 0. Okay, so is there a different z value that I might want to use? Is there a different z value I might want to use? I don't have to use the trace that's directly on the plane. I could use a trace higher up. The traces just have to be parallel. Okay, 1, let it be equal to 1. There's actually a better choice here than 1. Let's let z equal 4. Okay, let's let z equal 4. 4 is equal to 4z squared plus y squared. Now, why is 4 a better, or this is x squared, sorry. Why is 4 a better choice? Because it's the product of the coefficients of x squared and y squared. And when I divide by 4, what happens? Don't I end up with an ellipse? Does that make sense? Like, oh, dude, that becomes an ellipse. So if I let z be 4, then I can just turn this thing into an ellipse. Okay, well, where's z equal 4? 1, 2, 3, 4. This becomes an ellipse. It goes out in the x direction 1, and it goes out in the y direction 2. And so we just get our ellipse here. It looks like that. Okay. Okay, what happens if we let, say, x be 0? Let's let x be 0. Okay, again, this is still a trace. It's parallel. The trace doesn't have to be on the xy plane. It just has to be parallel to it. Okay, so this is our trace when z is equal to 4. This is our z equals 4 trace. Okay. So what about when x is equal to 0? Let's look at what happens when x is equal. We get z equals y squared. Oh, that's interesting. What do you think z equals y squared is? What is that in the zy plane? Well, where is the zy plane? Well, the zy plane is z and y. That's the zy plane. So what is this? Isn't this just a parabola? Wouldn't that just be my trace in the zy plane? Right? Yeah, what about, let's let y be equal to 0. Then isn't that just z is equal to 4x squared? So in the zx plane, what is this going to be? This is going to be 4. Okay. So we're getting this cup, right? We're getting this cup shape. And this cup shape is called an elliptic paraboloid. That's an elliptic paraboloid. Okay, let's do one last one here. Elliptic paraboloid. What time we got? But we don't have time for one last one, do we? What time is this? Oh, we got 10 minutes. We got 10 minutes? Oh, we could do this in 10 minutes. We got 10 minutes. It's all good. Okay. Let's sketch this guy. I'm going to call this number 5. I don't know what number we're on, but 5 is good. Okay, sketch. Z is equal to y squared minus x squared. Okay, so let's look at our traces here. Okay. Okay, if y equals 0, then what do we get? We get the parabola z equals negative x squared. Parabola. Okay, so let's look at that for a second. If y equals 0, okay, we get the parabola z equals negative x squared. That's an upside down parabola in the xy plane. Upside down in the xz plane. That's upside down parabola in the xz plane. Okay, that's good. That's good. I can deal with that. I like that. Okay, in the xz plane. I don't know. Maybe I'll bring it down again. A little further. Who knows? Who knows? Okay, so just right. So think of this like, parallel to that, right? Okay, it's all good. It's going to work out. Okay, what about if x is 0? Then what do we get? Then we get z equals y squared, which is still a parabola. So if x is 0, we're in the yz plane, and that's a parabola. That's just, oh, that's my friend, the parabola that looks like this. That's this parabola here. Okay. However, these two parabolas are at 90-degree angles to each other. Okay, this this parabola is 90 degrees to this one. Does that make sense? Those parabolas are 90 degrees to each other. They're like this. Okay? 90 degrees to each other. Keep that in mind. Those parabolas are 90 degrees to each other. Okay. Now, when x and y are 0, what's z? Well, z is 0 too, right? Does that make sense? When x and y are both 0, then z is 0. That is not going to really help us much. Okay, to know when is z 0? Well, when z is 0, x and y are 0. Does that make sense? Nothing there. So we're going to do a trace of z equals 1. So when z equals 1, what do we get? We get 1 is equal to y squared minus x squared. And what is that? That's a hyperbola. Okay, that's a hyperbola. Okay, that's a y-facing hyperbola. So at 1, I get a y-facing hyperbola, and it looks like this. Let's call this z equals 1. Okay, let me get rid of this because it's going to get in the way of my picture. Okay, and then over here, I get the other part of that hyperbola. Okay. I need to go out more here. Out further. Out into the spot. Okay. You get the idea. Hyperbola. Get some parallel lines going. Hyperbola. There we go. Boom. Nice. Hyperbola. This is at z equal. This is the trace at z equals 1. Okay, so now let's look and see what's happening. What's happening when z is negative 1? Okay, when z is negative 1. Well, then we get negative 1 equals y squared minus x squared. Multiply through by a negative, we get 1 is equal to x squared minus y squared. Oh, okay, so this is in the opposite direction. So at negative 1, when z is negative 1, we see this guy here. We have this guy down here. Okay, this is an x-facing hyperbola. Okay, an x-facing hyperbola. It's kind of weird. Okay, x-facing hyperbola. Okay, so I'm going to try to not screw this up too badly, but I'm going to draw a line down here. I'm going to draw a line down here. Okay, so far so good. Okay, this one's going to be a little harder. Okay, let's go out a little bit more here. Okay, and then I'm going to draw this line. Where do I want that line to go? This is along my x direction. So I really want this to go more like so. Okay, and then I want to connect. I'm going to get rid of this one. I don't like this guy here. He's making my life too much of a living hell. Okay, so that goes there. Then this is going to go down straight. Okay, and this guy I'm going to make go like this. Okay, because this guy and this guy should eventually meet, but they're not meeting for me right now. I'm not very happy based on the perspective. That's that guy there. Okay, and then this guy comes down. Okay, as well. Okay, and this guy is going to meet this guy. And like so. Ah, I didn't want to do that. Okay. So, and what this is called a saddle point. Or sorry, this is the saddle point. This is called a hyperbolic paraboloid. This is a hyperbolic paraboloid. Okay, now I did my greatest attempt at this. Okay, this hyperbolic paraboloid. Okay, hopefully you get the idea. I mean, I could probably do this better if I really tried. I don't know. Let's bring this down. Okay, and then based on the perspective, I don't know. It's just, it should just be, I don't know. Screw it. It's good enough. Okay, it's good enough. Good enough. It should just be something like this. I don't know, like that. I'm guessing. Okay, you get the idea. You get the idea. Okay, it's all good. It's all good. Okay, I think I went down too far on this side over here, but it's all good. It's all good. Okay. Okay, so that's called a hyperbolic paraboloid. Okay, now theirs is a whole hell of a lot better than mine, right? Look at that. Look at that. That's what I just drew. That's great. Here's the traces. Here's the traces. See, there's the traces. There's the traces in Y. There's the traces in Z. Isn't that amazing? Right? Little computer generated graphics. Okay, and then you're like, well, that's my hyperbolic paraboloid. At 0, 0 here, at the origin, it's called the saddle point. Okay, because it looks like a saddle. Okay, looks like a saddle, like you put on a horse, saddle. Okay, the saddle point where the concavity changes from concave down to concave up, that's called a saddle point. Okay, so 0, 0, 0 is a saddle point. That's the very last thing that you want to write in your notes there is 0, 0, 0 is a saddle point. Okay, so I'll write that in my notes before I leave the meeting here. Okay, so 0, the origin, 0, 0, 0 is a saddle point. And this is where concavity changes based on the trace. Okay, changes based on the trace. Okay, that's it. That's all I got for today, people. Keep it real. Keep it spicy. Okay, but don't keep it real spicy.
Thank you. Bye.
Welcome. Bye.
Thank you, Professor.
Okay, see you later.